I want to look at a couple examples here of related rates so that you can see how this all applies and how we put it in context. And so the first example here is a ladder on a wall. And so you can read through this, follow along with me as we read. A 3-meter ladder is leaning against a wall. If the top of the ladder slides down the wall at a rate of 1 meter per second, how fast is the bottom moving along the ground when the bottom of the ladder is 2 meters from the wall? So what are we looking at here? We're looking at a relationship between where it is on the wall and where it is on the ground, right? Just take a minute to look back, make sure that makes sense. We're comparing where it is on the wall to where it is on the ground. So our ladder will look something like this, and we know that this ladder is 3 meters long. So now, let's call this value y, because we're used to kind of looking like that in math, and this value x. Well, if you look, there's always going to be a right angle between the ground and the floor. So in other words, we know that y squared plus x squared will always equal to 3 squared. So this is our first step. We related the two quantities, x and y. Now let's take the derivative and see what we get. Well, we're going to get 2y times dy by dt, because we're talking about things moving with respect to time, plus 2x times dx by dt equals 0. So we've related the two rates here, because now we have dy by dt and dx by dt in the same equation. And these are just how fast the ladder's sliding, right? Change in position, change in time, change in position, change in time. It's just we're talking about, change in vertical position or change in horizontal. We wanted to solve for how fast is the bottom moving. So that's our x direction. So we want to solve for this dx dt right here. So doing some math, we get 2x dx dt is equal to 2y, negative 2y, dy dt. The 2's can cancel, and we get dx dt is equal to negative y over x dy dt. So now, what do we know? Well, y is moving downwards at a rate of 1 meter per second. So I'll be able to plug that in a minute. Is equal to negative 1 because it's moving downwards. We know that x is equal to 2. And hold on a second, we don't know y. But if we come back up here to the top, we can solve for y. So I'll leave that as an exercise for you to, well, actually, we'll do it together. So we get dx dt is equal to negative square root of 9 minus 2 squared, because that's our x value, and this is just rearranging that. In the denominator, we have 2, and then on the right, we have negative 1 meters per second, meters here, meters squared, dx dt. If you work through that and kind of play around with it, you'll get 0.893 meters per second. And if we check our units, 9 meters when it gets squared, because it's 3 meters squared. 2 meters that gets squared. Let me clean that up. It's hard to read that. Oops. I don't know if I can bring that back. Doesn't look like it. Well, luckily, because this is a video, you can rewind and go double check that. But let me rewrite that last equation for you here. I believe we had dx dt is equal to the square root of 9 meters squared minus 2 meters squared. That's for solving for y. Negative out front, 2 meters on the bottom, negative 1 meter per second here. And then all I wanted to say was this left meters squared, square rooting gives us meters, meters over meters cancels, and that's why we're left with just the meters per second units here. I believe I wrote the approximation there. Again, rewind, check out the work, let me know if you have questions. Our second example here is a growing cube. So I have a cube that's getting bigger over time. The side of a cube increases at a rate of 0.5 meter per second. Find the rate at which the volume of the cube increases when the side of the cube is 4 meters. So we want to relate the side of a cube to the volume of a cube. So volume is equal to a cubed, right? If we imagine a cube like this with side length of a. So this is our relationship between those two quantities. Take the derivative, we get dv dt is equal to 3a dA dt. And that's just, again, chain rule, 3a squared dA dt. And now we wanted to solve for the rate at which the volume increases. Oh, nice, it's already isolated, so it's just a matter of plugging things in. dV dt is equal to 3 times 4 meters squared. And then we said dA dt is 1/2 meter per second. So 3 times 4 squared would be 3 times 16 divided by 2 would be 8. So that means we get dV dt is equal to 24 divided by 2. So that was right, 24, because it was 16 divided by 2 meters cubed per second. Those units make sense because the volume is measured in meters cubed, and as it gets bigger, we're looking at a rate with respect to something of time, so seconds lines up nicely. This will hopefully make a lot more sense once you jump into practice, but as you run into questions, please do ask, and I'll be happy to provide that assistance.